Have you ever wondered what makes your computer tick? What makes it think, calculate, and run all your favorite programs? The answer is the CPU, or Central Processing Unit. Think of it as the brain of your computer. Just like your brain controls everything you do, the CPU controls everything your computer does. It's responsible for processing instructions, performing calculations, and managing data. Without a CPU, your computer would be nothing more than a lifeless box of circuits. CPUs are complex pieces of technology, but don't worry, we're going to break it down into bite-sized pieces. By the end of this journey, you'll have a solid understanding of how CPUs work their magic. Get ready to explore the fascinating world inside your computer. Let's crack open this CPU and see what's inside. First up, we have the control unit, the boss of the CPU. It fetches instructions from memory and tells other parts what to do. It's like the conductor of a bus, making sure everything runs smoothly. Next, we have the Arithmetic Logic Unit, or ALU. This is the math whiz of the CPU, handling all the arithmetic and logical operations, addition, subtraction, comparisons, etc., meaning the ALU crunches the numbers. We also have registers, small, super-fast storage locations within the CPU. They hold the data and instructions that the CPU is currently working on. And of course, no CPU would be complete without a clock generator. This sets the pace for the CPU, synchronizing all its operations. These are just a few of the core components that make up a CPU. Each part plays a crucial role in executing instructions and keeping your computer running. Now that we know the players, let's see how they work together. CPUs follow a step-by-step process called the instruction cycle to execute instructions. First, in the fetch phase, the CPU fetches the next instruction from memory. It's like reading a recipe, one step at a time. Next, in the decode phase, the CPU decodes the instruction, figuring out what it needs to do. This is like understanding what each step in the recipe means. Finally, in the execute phase, the CPU performs the actual operation. This is like actually baking the cake, following the instructions. This cycle repeats billions of times per second, allowing your computer to perform complex tasks incredibly fast. Just like having more chefs in a kitchen can speed up cooking, having multiple cores in a CPU can significantly boost performance. Multicore CPUs have multiple processing units within a single chip, allowing them to handle multiple tasks simultaneously. Each core can work on a different instruction stream, like having multiple chefs working on different dishes at the same time. Multicore CPUs have become the norm, powering everything from smartphones to supercomputers. Just like a bustling city needs roads for transportation, a CPU needs buses for communication between its different parts. The address bus is like a postal address system, carrying the addresses of memory locations where data is stored or retrieved. It's like the CPU sending a letter specifying the recipient's address. The data bus is like a highway, carrying the actual data between the CPU and memory. It's like the mail truck transporting the contents of the letter. The control bus is like traffic signals, carrying control signals that regulate the flow of data. It's like the traffic lights ensuring smooth traffic flow. These buses act as the communication highways within the CPU, enabling seamless data transfer and coordination between different components. CPUs generate heat, especially when they're working hard. Just like you wouldn't want to overheat while running, CPUs need to stay cool to function properly. Dynamic voltage and frequency scaling, or DVFS, is a technique used to adjust the CPU's voltage and frequency based on its workload. When the CPU is idle or under low load, it lowers its voltage and frequency, reducing power consumption and heat generation. Sleep states are another power management feature. When the computer is idle, the CPU can enter different sleep states, reducing its power consumption even further. It's like putting the CPU to sleep when it's not in use. Effective power management is crucial for extending battery life in mobile devices and reducing energy costs in data centers. It's a win-win situation for both users and the environment.